Can you guys hear me okay?
Absolutely. Welcome, Papa.
Thank you. Forgive my being late. I had my setup's been challenging me lately, and I had to fix it back. I got a new laptop for the new job and had to change things a little bit. All right, I'm glad you guys are here. Who has some some NumPy questions for me? And I hope you got to watch the original lecture that Hugo, Sun, and I did before for an introduction to NumPy. This session's going to be a little different than anything Hugo and I have done before. We're going to try to start out with pure questions, and then if you guys don't have any, what we'll do is I'll go into what I would have imagined you would have asked. So let me share my screen. And I'm gonna just, Hugo, I need you to let me share my screen.
Oh, I am so sorry. I am
No
so
worries,
sorry.
no worries. Yeah, no worries at all. Also, my lighting system is inferior this morning. Let me know when you've done it.
Yeah, done, sir.
Okay, great.
Yes.
All right, let's share. It's probably best to share the whole desktop. There we go. Excellent. So I want to show you well, let me see if there's questions first and then we'll go from there. But I've got this browser window open for starters.
Right.
Oh, and let me open the chat too, right?
Right.
I can see if someone's wanting to ask in the chat. And a hearty good morning, at least good morning from my side of the earth, my corner of the earth.
I think some people are already I know from the mail I sent. Yeah, I told them that you were going to show us
Forgive me,
something.
I have just woken up. So let's see. Okay, I don't see any questions in my email.
Yeah, I told them you were going to show us something magical about eigenspaces and eigenvectors.
We can do that too. So let's do this, guys. I just want to show you a process by which you're starting out, you don't know anything. And so I'm just going to imagine I'm you doing that. NumPy, linear, algebra. Oops, I'm still learning to spell. Routines. Now I could have written tools or methods. It doesn't matter. You start with something, and if that doesn't get you the results you want, you keep searching. Well, this took us right to numpy.org, a really good place to land. And just so that I keep this tab untouched, I'm just going to right click and say open link in new tab. And so I don't mix it up with this other window, I'm going ahead and bring that down here. And Hugo Sun, let me know if I should increase my resolution for any reason.
Yeah, I
I
think
know
it's
this
fine.
might. Okay, good.
It's great.
So we've already got some good verbiage here to start getting into, hey, how do we use the linear algebra stuff? Well, you see, they've made a whole module for it, linalg. And look down here. Some of their more popular routines and SciPy library also contains linalg module. So we can bounce back and forth between those if we need to. But notice that the SciPy has an eig. for eigenvalue problems and a solve. And both of them have a solve. A solve meaning I've got a system, which is an array of numbers that defines a system, which could be a group of data or potentially a data science problem. But and if we start going down, it gives us many methods in this modular classes. We've got the mate mul function. We've got a multi-dot, meaning we can send in a group of arrays and get their dot products. We can get the vector dot product of two vectors, the inner product of two arrays, the outer. And if you don't know what these mean, you're just a search away. You're thinking, well, what is that? What is the inner product of two arrays? Yeah, we'll just say vectors first. Well, here it's illustrated, even in just this picture. 2 times 8, 7 times 2, 1 times 8, and that would give you the new array. Or if you wanted to do the complete dot product, you then sum those products up and you get that. So you could do that with all of these. You're literally just a web search away from the answer. Now, I'm going to just tell you guys, what's a tensor dot? Compute tensor dot product along specified axes. Well, you have vectors, which are basically either a 1 by n or an n by 1 matrix. You could look at them that way. Or, but then you can have a matrix, which is n by m. Then you can have a tensor, which is a by n by m, or even more. So tensors are just basically more than two-dimensional matrices. In fact, I would have been happier had we not had a separate name for them, but that's the history of the math. And as someone tears apart my reasoning, they may sway me to think, no, it would have been better. It's better the way it is. But now we get down here to eigenvalues. And so once we've imported the linalg module from NumPy, we can call eigen or eig and compute the eigenvalues and write eigenvectors of a square array. Well, what are the right? Oh, now I just violated something I shouldn't do when we're doing this. Let's right-click that and open the link in a new tab. And now we can see, excuse me, that we compute the eigenvalues and write eigenvectors of a square array. So what is A? It's the only parameter we need to send in, and matrices for which the eigenvalues and right eigenvectors will be computed. Oh my, you can send in a tuple or a tuple, I don't really know how to pronounce that word, of matrices. And it will give you the eigenvalues and right eigenvectors for every one of them. But typically, we're only sending in one. And then, but it returns the eigenvalues, each repeating according to its multiplicity. The eigenvalues are not necessarily ordered, so the resulting array will be of complex type, unless the imaginary part is 0, etc. So now, I don't know if any of you are already thinking this, but you may be. Well, I thought these were called principal component analysis values. And,
Yeah, that's what I wanted to say. PCA.
Yeah, yeah. And what we can do, I already have a notebook prepared for that. And wanted to show you something very interesting from that. But please understand, if you want to do what I encourage you to often do, which is play a lot. Go and understand it at its lower levels. So when you step away from Scikit-Learn and you want to break things down yourself without always depending on the Scikit-Learn routines, the first level of depth you can go to is Numpy. And understand, Numpy is a foundation to pandas, to SciPy, to Scikit-Learn. All of them are using that. So if you are using Numpy, so if you want to go the next level down, like start to code like a Scikit-Learn programmer might do, you go into Numpy. And let's say, why would I want to do that, Thom? Well, you may not want to do it right now. What you want to do is, let's say you've gotten really good at PCA and you understand it, but you think, I really want to code it at a lower level. I want to understand the math, and I want to write my own version of Scikit-Learn. And why would you do that? To understand it more deeply. And why would you want to understand it more deeply? So you know better how to apply it. When you run into particular issues, because you've studied at that deeper level, you now have a clue about what you need to do. And then one thing I've done is write my own linear algebra routines without even using Numpy. And I built up classes because I wanted to see what it felt like to replicate without looking at their code and get the same answers, to replicate what Scikit-Learn does. And it's really helped me understand things better too. But again, as you're filling out your learning plan and you're going through the things you want to learn how to do, you don't have to learn how to code from scratch and derive the math from scratch right away. It's just that on certain routines, it's a good idea to do that, at least on some things. I strongly encourage anyone to develop linear regression from scratch, and logistic regression from scratch, neural networks from scratch, and decision trees from scratch. And then once you've done decision trees, you can figure out how to write your own random forest. Again, a deeper understanding will never let you down. It will always help you somewhere down the road. And you may decide to wait until you need that deeper understanding. My only encouragement is, don't wait too long. If you're always waiting when it's an urgent need, then it's slowing you down in the face of that urgency. So this is why we are always learning together. But let's start at a higher level. And let's go to this great, and I'm going to go a little bigger now. We'll just go up to my 100%. Usually run at that smaller level. And by the way, I don't see any questions. So I love this age that we're in, where we're doing everything worldwide with Zoom and Google Meet and stuff like that. The downside is I'm not looking at faces in my class, and I don't see the reactions. But I've been encouraged so much that I feel like, just keep doing your best, Thom. You're helping people, which is what I really want to do, and they're getting it. But please do ask questions over here in the chat, or come off mute and interrupt me and ask, because what I'm trying to do is help you. And even if you're not sure how to pose the question, let's work through it together. Just say, Thom, I'm confused. Okay, help me know where you're confused. And it may be that you're lacking context. And you know what? I get that. I completely get that. So just let me know, because you may have the same level of confusion as everyone else. Now, I modified this notebook from this article and its notebook. So let's see, Yuko, would you check? I don't think this Diamonds PCA is necessarily in our directory, but it
Okay, I'm
might
going
be.
to check that.
Thank you, Yuko.
All right.
By the way, I know you all care about me too. There's not a mean person in our family. So if someday we're doing one of these and you have to tell me, Thom, that didn't help me at all, that's okay. I need to know that. But I think we have a mixture of levels of readiness too. So I just want y'all to not be afraid to tell me that was way over my head. And then at least then I can tell you, oh, you want to go learn these things next then. And you help me survey our friends in this class too. It may be that we need to go through basic linear algebra.
All right.
I think we did, we did some of that in the intro to NumPy class, but not, I don't think we did enough. So
Okay.
it could be that after we do this one, everybody agrees, oh, let's do an intro to linear algebra. And linear algebra is beautiful, guys. It really is.
All right, Papa.
Okay, is it there, Hugo?
I've gotten it yet. I'm still checking.
Oh, okay.
But as soon as I do,
I'll
I'll
go.
send you a message. Just go on.
Oh, perfect. Okay.
Right.
So pandas is always handy. We almost always import it, but if you know you don't need it, don't worry. NumPy Seaborn provides, in fact, if I were, again, I leveraged this notebook. I didn't write it from scratch, but I'm going to lower that one. I like to me, Matplotlib is the backbone to Seaborn. And then I'm going to just put a little break in here to say now we're going to import various scikit-learn modules, the pre-processing, the model selection, and then PCA, principal component analysis, is in the decomposition module of scikit-learn. Now, the columns for this data set are going to be, this is about diamonds. It's going to be caret, cut, color, clarity, depth, table, X, Y, Z. I don't even know what those are, by the way, but I believe they're XYZ measurements of the widest points of the diamond in a three-dimensional plane. And then the price. And this is our label, just so you know. Now, we've got a URL to get the diamond data. It's been reduced here to make it simpler. And then we do a pandas read CSV, and it can take in a URL, which is awesome. And then you use columns equal columns. Now, be careful. This might have changed. And what we'll do is go through this notebook and then come back and try to run it just in case there's problems. Because if I start running it and something's changed, because this looks suspicious of me, to me, it might be that I'm just, this is a deprecated name in the read CSV, but we'll find out. So then this will load into a data frame. And I usually call them DF, but I leveraged this notebook and kept their terminology. Then data equals data calls. It's just going to reorder the data. So basically, when we put these calls in, it's taking the same data frame, it's just reordering them according to this order. And then we can print the shape, and that's the output for the shape. Now, there were some text in there, and you can see these authors have a love for pandas ordinal encoding like Thom does. So they put the dictionaries for replacement directly in here for the replace method on the data frame. And they said anytime you see fair, it's a 0, good a 1, etc., all the way up to ideal. And then, but then there was color too. So there's D, E, F, G, etc. These are this is a qualitative scale again. So they ordinal encoded these. And then there's clarity. And I remember way back when I bought my wife's engagement ring. This was many years ago. You probably weren't born. And I learned all these things at that time because I realized this is a family investment, this diamond. So I had to learn about clarity and quality. And I realized, okay, I'm not rich. I'm not buying the best quality or clarity, but you still get something if when you spend that kind of money, you want to make sure that stone is going to appreciate. And so anyway, then we can orderly encode these, or meaning qualitative, do the qualitative replacements from text to numbers. Now we have a complete numeric data frame. And now this can't be overemphasized. You want to scale your data anytime before you use PCA. There are many reasons I will always scale my data. Now, you may say, well, Thom, some modules, some algorithms don't require you to scale your data to give you accurate results. And you know what? That's absolutely correct. But I care about the whole pipeline when I'm doing modeling. I care about all the insights I can get before I get to the predictive modeling. And there are going to be steps that I do that do depend on scaling, and PCA is one of those. If you don't scale your data, all of the information you're going to get from PCA is going to be confused. So what's great is we can do, remember, in Scikit-Learn, when you're using the conditioning classes like scaling, you can do a fit, a transform, and then you can do a fit transform all at once. We only do fit transform on our training data. When we have set aside a test data set, we only want to do the transform method on that. We don't want to refit it. Do not refit it. That would defeat the purpose of making sure your routines generalize well. Okay, now that we have that, what the scaling class that we instantiated does is it returns a NumPy array. But we want to go back to pandas so we can use this great correlation method that applies to data frames. So no problem. We create a data frame. Oh, by the way, Thom can't remember everything. I think use columns is like, hey, you're going to see some columns coming in to this data set, but use these columns instead. And then here, when we call data frame again, well, this is kind of like calling data frame. It's just loading the data into a data frame. But here, the data frame itself, we're going to say columns equal calls. And so we can put that NumPy array right there and define the columns again. So again, we started with a data frame. We're just doing this one extra step to get a data frame again so we can do this great thing. And we're going to have that return core. So create a correlation map and create a correlation and map it out to see collinearity. So, and again, why would we use PCA? You're about to see. So plot the figure. That's what we're doing here. And then do the heat map. And that's what we get right here. Now, look at all this collinearity. Well, how do you know you're seeing collinearity? Well, when you see these very high values right next to the diagonals, or anywhere actually, that means X is heavily correlated to caret, or here, to caret. X, Y, and Z are heavily correlated to caret. That's what that means. And you can see over here that X, Y, and Z are highly correlated to each other. I want to caution you too. These are telling us the exact same information as these. And this triangle here is telling us the same exact information as here. In fact, it would be very useful if someone ever programmed, and I just think no one's taken the time to do it, but if anyone would ever program a upper triangular or lower triangular matrix, because we don't need both triangles of this matrix. All right. Now, if we go into Stats Model API, this is very instructive. It starts to show us that, well, based on what I'm seeing here, if I do a p-value analysis, these two are not looking as surprising as the rest of them. And I would like to see more decimal places some of the time, but these actually are pretty good. And you can see too, wow, this coefficient, its confidence interval, it didn't include 0, but it's very close. And this one definitely included 0. So we got a hint of collinearity by two methods here. This method of seeing these highly correlated values and using p-values. So you go and I will make sure that this notebook is in our shared directory if it's not there now. So how do we perform PCA on this data frame? Well, we still take our scaled data, but look at what I'm doing here. Now, this is a NumPy trick. This is saying use every row and use all the columns except the last one. So this is going from the beginning to now. Let me remind you what these colons mean when you see a NumPy indices. The first is you could have a number for start. So when you see this, it equals 0. And then if I say, trying to think how to make this very clear to y'all. This next one is the step size. Excuse me. It goes, I should do it this way, sorry. Start, stop, step. But this colon is shorthand for do all of them. And we needed to do that because we're going to break this up. But, oh, you know what? I think it's, forgive me. We'll double check this. Oh, darn it. I think it's start, step, stop, but we'll find out. You could do a little experiment to make sure. Now, what I'm doing here is say stop before the last element. This is when you use negative, NumPy saying, oh, you're looking from right to left now, or from bottom to top. You're going the opposite order. And this is saying come one in. So it's basically saying start at 0. When you don't include the other two colons, you just include one. It's assuming, oh, you want to go from 0 to just before the last element. Or if we put a 2, just before the second to last element, like if we had 2 labels. So just wanted y'all to be clear on that. And then forgive me, I don't know why this is also here. If this is here, apply PCA to all but label. That's what this would have done. So this does look redundant here, but we'll keep going. Oh. We will have to rerun that then. So we'll get this notebook running. I was hoping to avoid that just in case there's problems, because if this link is broken, we'll have to go get the data together. Yay, it did fine. And we can rerun this guy and get the same pretty much results. Okay, so we have a problem here, and I suspect it's what I was just saying. So what I'm gonna do, I probably did a change and then did get back to this. Let's see. Oh, looks like I already had it. So let's comment that one. By the way, I'm just doing control/ to comment and uncomment, control/. Very handy to know in case you didn't know it. All right, I think that will fix that because we're saying applied all but the label, and I probably had this statement in. And let's see, in components. Okay, well, this may bust too, but we'll figure it out together. Yep, it's saying name PCA is not defined. Okay, oh, well, I need to do this instantiation first. And I probably commented that one out for some reason, but I believe, so all I'm trying to do here, the number of components can be obtained by just getting the second shape, meaning the number of columns. So let's look at this in more detail. And I think I'm being redundant here, but let's just add some more steps so we can see what's going on. So the first thing I want to do is just print this guy and its shape, okay? And I'm just gonna, we'll allow these a little bit at a time. So let's do that much. Okay, we've got that many rows and this many columns. Well, this is the number of components, but I don't want to include the label. So the next step I'll do is this one. And we'll get rid of these extra visualizations later. But now I want to do the same thing, but it's not XY scaled anymore. Now I'm just going to call it X, S scaled. And then I'm going to look at the shape again. And so, yes, I've only included the features, the inputs, not the label. But if I just want the number of components, I can do this trick. And now I get just a number because I said, well, in the shape, take the one component, which would be the columns. 0 would be the number of rows. So now I have that. And sure enough, I didn't need to do really that because that would have been redundant. So I really just want to instantiate PCA. So here's the PCA class, and I'm telling it this is how many components you'll expect. Now I could have also just said number of components equals this xc.shape. It's cheap to pass it in. And so that will instantiate. And then I need to, here I chose to do it in 2 separate steps. Again, you could do it either way. I just wanted to show people that you could do it either way. And so now we'll do, if we do that much, we're doing everything. So I'll go on ahead, now that we've seen those, I'll leave them there, but I'll comment them out and we can go on ahead and run all of this. Okay, we've got a lot going on here. Let's look at what's going on. The first thing we get is percent variance explained. Well, that comes from the explained variance attribute of PCA. And what we're doing then is taking the summation of the explained variance. So this is a vector, but this will return a the sum of that vector. And we're basically just scaling these, okay? And then we're looking at cumulative variance explained. So when you send in a vector like this one, it will instead return the first element. Then the second element of this will be the first plus the second element. And the third element will be the first plus the second plus the third element. So that's what when we look at explained variance, you see we get these values right here. But then when we look at percent eigenvalues, we're doing the next phase, which is all of those scaled by the sum. So we take the sum of these and we scale each of these values by dividing it by the sum. And that's how we got these, it says percent, but this is fractions adding up. If I sum these, they'll all sum up to 1. And then you see the truth of that. Here's the first one, but this is this one plus that one. And this one is this one plus those, etc. And then finally, with those cumulated eigenvalues, we're doing a plot of them. And we're seeing how, okay, they're going up, and whoa, when we get to 5, there's really not much value in the rest of these. That's what an eigenvalue is telling you when you apply it to a modeling problem where you're looking at the features. It's telling you, well, when I go into this magic eigenvalue space, I now have these eigenvalues and eigenvectors, and I'm going to show you how it's magic here in just a moment. But what does this mean? It means that in eigenspace, the 0th component and all the way up to the 5th, which is the 6th, they're significant. But the amount extra information you get for the 6th, 7th, and 8th are pretty negligible. Again, look at how small that's why we print all of these. These are the full eigenvalues. These are their scaled according to all, and you can see, that's got some significance. Okay, yeah. What we're looking at is 4%, 8% roughly, almost 11% there. But these,
Papa, I think there's a question from Nima.
Yeah, I'll get there.
Okay.
These are just very small. These are less than 1%. And you can see that dynamic here. We got up to almost 1 here. And then now we're just asymptotically approaching 1 right there. So what this is telling us is these last 3 eigenvalues and the variance they represent to any potential modeling, very inconsequential. Okay, I'll look at Nima's question. Nima, we're getting to that. It's like you and I planned for you to ask that question right then. Very good. Okay, so, well, okay, what you're telling me is we only need to use 5 components of those PCA components. Yep. And let's see what happens when we look at that. So we're going to do the fit transform again on our same X scale data. We're going to put that back into a data frame. We're going to look at a correlation matrix, and we're going to basically do what we did above. Look at this. We have this beautiful system. And there is look how small all these values are. But what does this represent? These aren't the original features. We're in a new space. we've kind of gone through a mathematical wormhole, okay? We've traveled to a new space, but it's funny. The new space is right over the top of the old space. It's just been changed to a perspective where there is no collinearity. What does that mean? All of these features are completely independent from one another. We call that orthogonality. We love that. That allows all our math to be super simple. But let's just look at something real quick. What would that have looked like if we had included all the components? So I'm going to say, no, I just want to see what it would look like for all 8. Oh my, that's completely, all of these are completely independent from one another too. I mean, these are tiny values. We call that 0. These are essentially 0 on, you know, all of them are close to 0, either on the left or right of 0, or the negative or positive. But, well, why do we want to reduce it? Well, again, parsimony. Parsimony is a beautiful concept. To me, when I think of parsimony in the artistic realm, I think elegance. It's a piece of art that's not too busy, but for the things that are there, it's perfect, it's beautiful, it's adequate. In modeling, it's saying, why would we use more features than we need? That just makes the model harder to explain. In fact, you really can't explain it as well if there's more features there than you need. By the way, we could get accurate predictions using all 8 of these, even in the original space. But there's so many insights we could have given or gained or explained to others and ourselves if we would reduce it to only those features that we need. But the only reason we're reducing the number of features is because of what we learned right here. 1, 2, 3. We didn't need those other 3. So we reduce the complexity of our problem because, sorry for scrolling so much. I hate it when others do that. These aren't giving us enough value to be concerned with them, is what we're saying here. So we would use in PCA space this one. But remember, we also get eigenvalues. So what are my eigenvalues? Well, if I do, now that this, I should have put more notes in here. A reduction in PCA eigenvectors does not remove collinearity if we transform back into the original space. So notice I'm doing a Numpy matrix multiplication. And I transform these, I've got the reduced PCA now. I've got the reduced data set, but I'm in PCA space. And these components, they're actually the eigenvectors. So I'm going to put those into a data frame. I'm going to use my columns minus the price. And by the way, this is just looking at this because this is a single dimension one. That's why we're only doing this much. Remember, columns is just the names of the columns array. And then I look at the correlation. Well, look, what I've done, I've transformed from eigenspace or PCA space back to the original space. I still have collinearity. In fact, what I've done is strengthen it. So PCA itself doesn't really do anything to the original space. We went to PCA so we could simplify the model. Now you may be thinking, well, oh, then you've got the extra burden of doing that PCA. True. And you may not want to incur that. I think it's best personally to find out what's collinear and remove it. And then if you still needed predictions on those collinear variables that you're going to take out, well, you can do that. You can relate them after the fact. But this is just to show that just because you're in PCA space or eigenspace doesn't mean the original vectors don't have some relation. Now, boy, I wish we had Jonathan here today. I should plagiarize his material, but what he did was show, create a visualizer that he got from someone else that shows how these relate to one another. In other words, when you see PCA 0, it is actually a combination of original space vector 0, 3, and 5. I'm making those up, by the way. But there is a way to relate. Oh, when you use PCA 1, that's this level of combinations of original space 1. And when you look at PCA 2, well, that's this combination of original space vectors or features, I should say. So these are now PCA features. They're not original space features. But again, why would you do this? Because now you have complete independence of your features and you can clearly reduce it, and then you can get very good predictions. But what we've lost, not completely, is how this relates back to original space. It's not that we can't relate it, we just have to do a bit more work to relate it. So I would say, if you guys have liked this, what we'll do is go through the math next time to visualize that what I was just talking about, how we can relate these eigenfeatures back to original space features, how they relate to one another. And I think that's super powerful because there are many times we could want to use PCA, but we never want to lose the insights of how does this model relate back to the original space. I mean, there may be rare times where you only care about the prediction. And if that's the case, you know what? You didn't need to do any of this. You can get accurate predictions using all these features. But personally, I always prefer to go through the discipline of either figuring out what shouldn't be there and explaining that, and then using, for example, here, I'm pretty sure I'd use all of these features here, but I would not use X, Y, and Z. I mean, if we continued to do the analysis, I'm pretty sure that would be the conclusion I came up with. And you could remove this one, X9, and rerun this p-value analysis, and it would change. And you might find that this one is now much bigger. And you remove that one and you rerun it, you might find that this one is now big, until you realize, okay, I've got a p-value analysis where all of these are 0. But also I'm rerunning this correlation matrix. However, did you just talk us out of using PCA altogether by doing more work to reduce the features that are collinear to one another and only retain one of those collinear features? No, I would still be inclined to look at PCA both with and without, you know, with these bottom 3 and without them. You don't know ahead of time which model is going to be best, and you're testing not just for best model accuracy. And I really want y'all to get this down. I got this great question over LinkedIn. A young woman from Tunisia who likes to ask me questions on LinkedIn. She said, Thom, how do I compare models? Well, with metrics. You want to be really good with your metrics. So there are metrics for accuracy, but then there's parsimony and generality, and those are a bit less crystal clear. But what do we mean when we say them? Well, I mean, accuracy is important, but if I do a cross-fold validation, and that means I'm giving every portion of the training data a chance to be the test data. I don't want the model that was the most accurate on one of those folds. I want the model that's got the best kind of a ratio of best average accuracy divided by the standard deviation of those accuracies. Why? That tells me that the model's going to behave similarly when new data comes in. We want a model that doesn't just work well in the training data, it works really well in the test data too, because that's our only way to look for generality until we test the model in completely new data. So, but again, one of the ways you get there is not always, but a lot of times, the real reason to get rid of the collinear variables is so the model's more explainable. Until you get rid of those, it's harder to explain things. But don't make the mistake of thinking that you're getting rid of the collinearity in the original space because you did this. I would test the model accuracy in a generalized sense for both this version and this version. Okay, I hope I haven't lost y'all. This is actually a bit of an advanced lecture. And if you don't understand eigenvectors and eigenvalues real well yet, doesn't mean you couldn't understand any of it. I just want y'all to not beat yourself up if you couldn't track this yet. Just say, okay, what did I learn? Take something away. What you learned was that when you apply PCA, you go from something like this, where you have collinearity, into a magic space where there's no collinearity. And there is absolutely a way to relate these features back to the original space features. But why would you want to do this instead of that? Because it gets rid of the collinearity, which typically, but not necessarily always, will help you generalize better. What does generalization do? It makes sure our models work well on new data. Okay. Let me know in the chat. Did this help? Was it a good start? And Hugo will help me figure out with you guys where we want to go next.
Yeah, I think I would just create a poll right now. I think we probably would first take one of those courses on linear algebra. So I will just create that right now. Then one more thing I wanted to ask was,
yes,
I wanted to ask, right now we have done this PCA on this data set. Now, if we were using a neural network to process this, would PCA still have been necessary?
That is a great question. Getting your data to a state like this, or as close as possible, I think is always super helpful. Because if I'm training a neural network with this versus this, I've won. This input reduces the number of parameters in that neural network model significantly. And in fact, that would be the motivation to get rid of collinearity, is to aim for that parsimony, that elegance. It makes the model easier to explain. And then we only have to go back and tell people, look, we're only including caret in the model because it's so strongly correlated to X, Y, and Z. And caret gives us more complete data about the size. So we can always just relate back X, Y, and Z along with caret. And anyone in your organization, oh, of course, yeah, we get that. Then we've got the type of cut, the color, the clarity, the depth, the table. So that, again, an elegant model, a model with good parsimony, a model with no collinearity is easier to train. It won't run into any mathematical problems, which with today's algorithms, they hardly ever do, even if you have collinearity in there. But again, an easier model will train faster. It'll train more reliably. It will typically generalize better, and it will run faster. This model, again, we're not working with a super complicated problem, so it wouldn't normally be a problem. But if we had many, many features because we're doing some deep learning, any way, any pre-work we can do to reduce our dimensionality is great. Dimensionality reduction is our friend. And we've gone too long. We need to get the guys got. But guys, please let you go and I know how we can do better. And I'm going to hang up rapidly. Sorry for that. And
Okay.
then hopefully I'll see y'all in his class. Oh,
Guy,
yeah, I'll go ahead and do this.
Yeah, Guy sent a message. I think he sent a message that he would not be around in class. So, yeah. So I think he sent that so that we can take as much time as we need for this class.
Okay, okay, but we won't rush off then. If you know for sure he's not teaching, we won't rush off. But yeah.
Right.
Okay, so would you want our next Saturday? Okay, good. 6 out of 6. That's great.
Okay.
And is there anyone that didn't vote?
Yes, there's still, yeah, there's 7. Okay.
Oh, there we go. 8 out of 8.
8 out of So I think we have a consensus already. Next Saturday we'll have to be on linear algebra.
Very good.
Right. So,
or as the Brits would say, jolly good, or the old Brits.
So we would have to really trash this eigenspaces and yeah, because I really want to. I tried wrapping my head around that. I tried using a matrix to solve it. Yeah, I know my linear algebra is very rusty, but I had to bring it back to to NumPy to, you know, yeah. Okay, so I'm Ravi. Ravi, please go ahead, unmute yourself.
Hello, Thom. How are you doing?
Hey, Ravi. Good. How are you?
I'm doing fine. My question is not particularly related to PCA itself, but it's something that you did at the beginning. So basically, when you were doing feature engineering, and specifically when you were ordering categorical variables into, like, giving it a label 1, 2, 3.
Yes.
Like in this case, you did it at the very beginning, but usually sometimes, yeah, exactly. That's the one.
So great. What's your, yeah, go on ahead.
Like, isn't it always advisable to do it after you do the train test split?
Oh, it wouldn't matter. You're still going to do the same replacement. It's completely independent of that.
Okay.
Now, what you may be asking, okay, so when we're doing encoding, it doesn't matter. I mean, you might as well just do it to the whole data set right at the beginning.
Okay.
But now the scaling, it matters. You would only do a fit transform to your training data, and you would only do a transform on your test data.
Okay.
And that's how that's one of the ways you're testing for generalization. Because you're realizing, hey, I'm not going to be doing a fit transform on the new data that comes in when I put this model in production or when we start using it on new data. So I've got to treat this test data set the same way. We're not going to do the scaling, every time we get new data. That would completely confuse the process. It wouldn't
Okay.
be legitimate. Yeah, good question. Who else?
Perfect. Thank you.
Oh, you're welcome.
And I actually have another question, but I'm not sure if I should ask it over here or in the next session.
Oh, go ahead and ask now, since we're not in a hurry.
Okay. Okay. So in some cases, this is not in the case of regression, but this is more in the case of classification. When we have a class imbalance, we usually either go for undersampling or oversampling, or most people right now use SMOTE. So when you do this, is it advisable to do it before train test split or after train test split?
Great question.
Like, because if it is the synthetic sampling, there are some points that the test data points can generate the synthetic, and as a result, there is data leakage to the trained data set. So which is the best practice for that in general?
Oh, this is a great question. So let's think it through together, okay, Robbie?
Okay.
So let's imagine we're in a real scenario with this. And we realize we have a class imbalance. Now, we need to train this model reliably. So we're going to use SMOTE or bootstrapping or some form of legitimate. And by the way, you could probably make up some other legitimate methods on your own. They just have to make sense. And it's always good to run it by other data science friends that you respect their knowledge, say, get their opinion. What I'm trying to say is SMOTE's great, bootstrapping's great, but random sampling with replacement's great. But you might come up with something you think would be a little better for your particular situation. But this class imbalance is a challenge. And so you're only addressing it to get a good model. And you come into a range of balance among your labels until you're confident you're getting a well-trained model. It's not overemphasizing the heavier class. You follow me so far?
Yep.
Okay, good. Well, now we've got the test data. Well, it needs to act like the real world data. And so, in my opinion, I would not want to balance the test data. And yet I need enough data to do a metric on, right? So I would tend to look at it both ways. If I like the way my weak class is getting a greater population, I'd like to run the test metrics with and without the balancing on the test data to see what the metrics look like. And if I'm getting fairly reliable metrics without the resampling or the SMOTE, I would stick to that. But why would I look at it both ways? Again, I want to test the model, but what's going to happen in the real world sense? Well, we started out with imbalanced data. That's because the process itself probably delivers imbalanced data. And so I need to also look at how the model's going to behave as the imbalanced data comes in, right? So again, I think it's most legitimate to test the model with the test set in the unbalanced state, but just so that we can get some metrics that make more sense, depending on the metric, we might need to balance that test set too, just for the sake of the metrics. But again, I would test with and without the balancing, because the imbalanced state is likely the real state of the ongoing data that you'll collect. Does that make sense?
Yes. Thank you so
Okay,
much.
good. Oh, you're welcome. Oh, and again, you know, Ravi, I'm asking you a favor.
Yeah.
I mean, as you move forward in life, this may be 10 years later. I'm pretty sure our Slack work group will still be running by then. I'm pretty sure I'll still be active on LinkedIn. Get back to me and say, Thom, I ran into a real world situation and this is the way it played out. And you may have to say, I need to correct you on some things you taught me. And I will say, thank you. I mean, guys, I want you to trust everything I say, but verify. In other words, don't just believe everything I'm telling you is absolutely the complete story and the absolute truth. I'm giving you my best answer based on my experience. But as you move forward in life, always trust, but verify, you know, because
Okay.
you might find a situation where, here's an exception. I'm going to tell Thom about this after I, you know, understand it better. And then maybe it's something that we collaborate on too.
Okay. Of course. Of course. Thank you so
Excellent.
much.
You bet. By the way, y'all, I had a habit. I'd go around and ask people smarter than me, or that I should say smarter, I should say, because I don't want y'all to look at me as smarter than you. I just have learned more. Doesn't mean I'm smarter. It just means I know more. But I'd go around and ask people that knew more than me, hey, I need to do this. Do you have an idea of how I should go do that? And anyone that took the time to help me, I paid it back. I'm always telling y'all to pay it forward, but I kind of figured it was kind of paying it forward by saying, you know what, they took the time to give me an answer. So I'm going to go back and either tell them, thank you. I just want you to know that worked perfect. Or, you know what, here's what I found really worked best. Now I've paid them back for the time they gave me. And that was always my hope, to say, wow, you gave me some of your time. I should share what I learned because you took the time to help me.